Assalamu alaikum wa rahmatullahi wa barakatuh. Dear student, today we are going to discuss a topic from energy sector, and that's the most important one. But before diving to the detail of this topic, first I will want to share some of the statistic of the world energy annual growth or just percentage of the annual growth. Dear students, keep in mind that the world total energy consumption uh, according to the Global Energy Statistical Yearbook is 14,000. Okay. That is 14,000 million tons. Keep in mind this term MTO is usually used that whenever we are dealing the energy at large scale, not at smaller scale, and it's very interesting term. And this 1 million TO, for your understanding, whenever we are dealing this, it is equal to 4.18 into 10 raised to the power 16 joules. So that's the unit that we are going to discuss this. Okay, so that's the total energy consumption of the whole world. In one of my presentation, I have already shared this information with you that if you take this amount and divide by the world energy population, so the average human being energy consumption, we can just calculate it is almost 2100 watt bulb. And that's not for 5 minutes or for 10 minutes, that's for 24/7. That every human being in this world is consuming energy on average level, that is 100 watt bulb. But that amount is not constant everywhere in the world, because this may vary from country to country. For example, I'm taking the case of USA. In USA, the average energy consumption per person is 110 100 watt bulb. So that is also for 24/7. So now here you can easily understand that for normal average human body, it is 21. But for USA, it's 110, more than 5 times. That's just the ratio. Okay. So now you know about the point that the total world energy consumption is 14,000 million tons, out of which we know that the statistic of the 2018 that the China is consuming, China is on the top most in energy consumption. For example, the China, I'm just giving you some figures and statistics. China is consuming 3,164. The second position is that of USA, and USA individually consuming 2,258, and the unit must be MTOS. It is million tons. Same for all. Okay. On the third number, we have the India. And India, individually, they are consuming 929 million tons. And then on the fourth, we have Russia, which individually consuming 800 million tons of energy per year. So that is the total energy consumption of the Russia. And then Japanese, which have 424. And then beyond that, we have South Korea 307, we have Germany 301, we have Canada 301. But the basic point that I want to make from this slide is you can just compare that if we combine the energy consumption of these three countries, so it's almost half of the world energy consumption. Okay, so that's one important point over here. The second important point that today we are just relying only on the fossil fuels. Most of our energy sectors, more than 80%, I'm just using a very careful figure, there's more than 80% we are on the fossil fuel. And we know that the fossil fuel is going to be down after 2050. According to the research of some of the researchers, it's not more than 2070. And we also know the second point, that there is a rapid increase in the energy consumption. And that is energy consumption rate according to 2019 report. That's the worldwide, the growth is 2.3%. That's the growth rate of the energy consumption year-wise. Okay. Now, if we just look at the individual countries, so it's vary from country to country. Now, for China is again on the top level, it's 3.7%. Then on the second position, we have USA. That their annual growth rate increase in the energy sector is 3.5. Okay. Now, it's also not astonishing that there are some countries whose that growth rate is not increasing, it's still decreasing. Although maximum, most of the countries, the growth rate seems to be increased. And that growth rate in the energy consumption sector is increased. That's not astonishing, because if we just compare our previous year or in the individual life, so the energy which we are consuming in the previous year is not exactly the same that we are using this year. So that's not astonishing. The most astonishing factor is for European Union. If we take the European Union statistics, so there is a -1% decrease. That's astonishing. For Germany, there is -3.5% decrease. So USA is going to increase its energy consumption. Germany is going to decrease its energy consumption. Now that's -3.5% partly due to the decreasing consumption in the power sector. Now a middle winter, reducing consumption, and energy efficiency improvements. So these are some figures that you should keep in mind, that before diving to this subject, we should at least know that the word energy consumption. Now, the first point, it's clear that energy consumption, let's suppose it's a broader range of energy consumption. Out of that broader range, only this amount of energy, that is a small portion that we are using from renewable energy sources. Renewable energy sources. Okay, and the rest of them, that is on the fossil fuels, which may not be available after some time, because we know, according to the world statistics, that the energy domain is going to double, the food domain is going to double, the water domain is going to double, which doesn't mean that in the near future we don't have water to drink. But the basic problem is that the water will be available, but water according to our requirement and according to our demand will never be available. That they might contain the essential nutrients, the essential minerals that they have, that kind of water may not be available, easily not available. So that's the reason. Now what should we do? Okay, being as a researcher or being as a chemist, is it possible that we can switch from that fossil fuel to some other factor, some other sources? That may be any source. So yes, there are a lot of options that we have. So today in this class, we are just discussing one of the option that we can switch from the fossil fuel to some other options. That is in the case of, in the form of fossil fuel cells. Now, what is fuel cell, how it work, what are the kinds of fuel cells, and how we can use in our daily life? Is it commercially available? Because there are a lot of perceptions regarding fuel cells in our society, that most of the people, they are thinking that it's not available. It's not possible to be commercialized. And some people, some educated people, still thinking that fuel cell is of no use. So in this lecture, I will try my best to discuss some important factors. But before discussing that, okay, let's once again, I'm coming here, that there are different terms like batteries and fuel cells. Batteries and fuel cell. There are some differences and some similarities between fuel cell as well as the batteries. And the first of all, I want to clarify that there are some similarities and differences. But first of all, the differences. What are these differences? Now, keep in mind, batteries is confined in a sealed container. We have a seal container, and in this seal container we have our electrodes and we have our chemicals. Now thus the capacity is measured in ampere hour, amp hour. That's the capacity. And now the second point, that we can also determine by the quantity of chemicals it's hold. If the chemical is good enough and they can completely oxidize or completely reduced, so then that's one good kind of batteries, and then we can easily take the electron. It means that the chemical energy is converting to electrical energy. Now, on the other sides, if we take the fuel cells, now fuel cell is a different scenario. Chemicals are supplied from external sources. We have, you can consider like a container. Inside that container, we have different plates, and then the chemical oxidants and the fuels, they are continuously supplying from the outsides, from other reservoirs. So the capacity is limited only by the available supply of the reactants. If the supply is continuous supply, then it's working good. Otherwise, it may stop. So for this reason, fuel cells are rated by their power output. Okay, and it's measured in watts. It's one sort of differences. Rather than the batteries is by capacity, but it is measured by its power. The second point you should keep in mind that fuel cell and batteries, you know that batteries is basically energy storage device. Energy storage device, okay? And the fuel cell, they are not energy storage device. What we can say, these are energy conversion device. So it stores energy and it converts energy. That's another difference. Now, another major distinction between batteries and fuel cells lies in the nature of chemicals employed. That which kind of chemical we are going to use within the batteries or within the fuel cells. Now, keep in mind, batteries, they're based on inorganic compounds. Inorganic compounds. And you know that they are basically metals and sometimes oxides. What about the fuel cell? They usually employ hydrogen and also methanol, and they can also use ethanol, and they can also other hydrocarbons. So these are the different, these different fuels, that is hydrogen, methanol, ethanol, are different hydrocarbons. Basically, they use it as a reactant at negative electrode. It goes at a, we have different plates, that's a positive and negative, so they goes as a negative plate. Okay, and oxygen, they are also using oxygen at a positive plate. So that is the difference between here. Now here, a provision has also been made for the removal of heat liberated during electrochemical reaction. Okay. There is also a lot of explanation, a lot of regarding that fuel cells, that the most important thing and the most connected term to fuel cell is the platinum. Platinum is important for here. Now, to demonstrate a principle of fuel cell at lower power output without the regard that it's cost, that how much it will cost, it's remarkably simple and it can be done in any school science laboratory. That's quite easy, because for that you need not sophisticated instrument. What you need, basically you need a beaker, and that beaker must contain some plates, some tube, and that tube contain a plate, and here you need to supply gas, and that is a hydrogen gas. Now you need also a medium. Inside that medium, what you will put, let's suppose you put potassium hydroxide, is okay. And then on other side, the same assembly on other sides, and oxygen is coming on that sides. Now there must be external circuit, so electron can move there and here, and oxygen can take the electron and convert to O negative. And this hydrogen and H2, which is now in the form of proton, H positive, they combine with one another and give us water. So that is a very simple assembly, and you can perform this sort of experiment in a very simple lab. It's not difficult. Now the issue lies whenever you are dealing it at higher level and you need a high power system. So when you need a high power system and that are at acceptable cost, sometimes we can get a high power system, but at a expense, the expense of that is not in the range that an average person can reach, can access to that. So then that is not acceptable. So that is a problem over here. Okay, the fuel cells, they usually function at a very low voltage. So that's the reason that we cannot use individual cells. We can make stacks of that cells and then we are proceeding that. Now coming to the basics of that. As we had already discussed that fuel cell is energy conversion devices. So here you can see that this is energy conversion of the chemicals into direct electricity. And that is in 1839, even 50 years before the advent of internal combustion engines. Sir William Group gave the idea and the first prototype of the fuel cell, and he designed the first fuel cell. And here you can easily see that that is the one side from which you can just enter any sort of fuel. And that fuel, uh, there must be an oxidation reaction of that fuel. Okay, so oxidation here I means just the removal of electron from that fuels, and the rest of that ion, that is, let's suppose hydrogen ion, is coming in that direction. Now on the other hand, you can see here is oxygen or any oxidant is coming on this direction, and they take that electron which is coming through the external circuit, and that electron is being consumed by that and converting into O negative. They combine both of them and you can get a water. So that is just the simple structure of a fuel cell. There is no complication in that. So now slowly and gradually we will move forward and we will discuss the type of fuel cell, the mechanism which is happening over here, but the basic structure will remain the same. Keep in mind, there must be electrodic, there must be a medium, there must be a fuel source, and there must be an oxidant. Okay. Now slowly and gradually we will just discuss one by one. Now there are different dozens of fuel cells, different kinds of fuel cells. But each case there must be something common. And this common thing must be an essential part of a fuel cell, no matter it is alkali fuel cell, phosphoric acid fuel cell, or solid oxide fuel cell, or any kind of fuel cell, ethanol fuel cell, whatever the case may be, but these components must be important. The first one, they need electrolytic medium. And that electrolytic medium, they must conduct ions. Now keep in mind, as I told you that in the previous slide, that a fuel cell contain a container that must contain different electrodes, cathodes and anodes, and they must contain some medium. Now that medium can conduct ions, and they may be porous solid that contain liquid. It may be liquid. It's not necessary that it must contain liquid, but it may contain liquid because it may be solid. In the case of liquid, it may be acid, alkalis, or fused salt. Now it may be a thin membrane, and that may be a polymer or ceramics. Now this membrane must be an electronic insulator. That is the most important point you should keep in mind. As well as good ionic conductor, and must be stable under both strong oxidizing and strong reducing condition. Now these are the conditions for this electrolyte medium. I want to expand it a little bit more. Now from here, you can also, from just this line, you can also classify the fuel cell in different kinds, that acid fuel cell, alkali fuel cell, and salt fuel cell. The first point that you should need to remember that the electrolytic medium must conduct ions and do not conduct electrons. They must be a good conductor, good ionic conductor, but must need to have bad electronic conductor. Why? The reason behind that is, if your medium, that electrolytic medium can also conduct simultaneously ions and electron. then it's not possible that you can draw electric current from that. It's not possible. So it must be insulator, electronic insulator, but good conductor. Let's suppose if it is not a good conductor, a good ionic conductor, what will happen? So the byproduct that we are getting uh, from the fuel cell, we are not getting that. Like in the previous slide, I explained that it just give water as a byproduct. So when it is not giving water as a product, so there must be accumulation of cations and anions over there, and the environment over there will be a highly acidic or highly basic, or there must be accumulation of these cations and anions. So in that vicinity of that cathodes, because if they do not conduct that, so what will happen after some time, we will have a lot of positive charge accumulating near one electrode and a lot of negative charge on our right hand side of the electrode. So that create a very unstable environment inside the fuel cell. So that is why we need that the electrolytic medium must have a good ionic conductor and must be electronic insulator. That's very important. The second is its stability is very important. For example, it's going to degrade during the oxidation reaction. So just after oxidation, we don't have that medium. What will happen? Now, if it is going to neutralize or going to change, chemically change after a reduction, then we don't need that kind of medium as well. So that electronic medium, the electrolytic medium is one important things, and it must be in every kind of cells. Now, the second point, that it may be a membrane. So if you are using a membrane, a polymer membrane, so in that polymer membrane is not stable under oxidizing agent, or they are not stable under reducing conditions, it's going to degrade or chemically react with that. Then of course, what is coming from the acidic, from the cathodic side or from anodic side, how they can going to mix, because you had already removed the medium. When the medium is not there, how the ions can mix with one another, how they can come into come closer to one another. So that's the big issue over here. So here, for all those students, particularly for PhD students, I'm just giving you a clue over here that if you are able enough to prepare a membrane, and that membrane is stable enough under oxidizing and under reducing conditions, and that's not difficult to test its stability under oxidizing agent and under reducing condition. That's not difficult. You can do it any simple way. And the preparation of membrane is not difficult. It's exactly the same that you are mixing some chemicals and you are casting all these chemicals on the hot plate. And after some times, it's exactly that you are cooking a bread in the houses. It's exactly the same. So then your membrane, you can just compare your membrane with the already existing membrane. There are some standard membrane as well. You can compare its activity with that one. And I told you what will be that activity. You should check that either it is electronically conductor or not. If it is electronic conductor, you should discard that. If it is electronic insulator, okay, you had achieved one goal. The second point, it's a good ionic conductor. So if it can conduct ions or not. If it can conduct ions, and what is its ionic conductivity? How much is its ionic conductivity? You should also know that. So there are a few parameters about its electronic insulation and its ionic conductivity, and how much is its ionic conductivity. If you can easily calculate, that. And if you are able that you had prepared a membrane that is electronic insulator, and they are good ionic conductors, and they are stable in oxidizing condition and also in the reducing condition, then I'm sure that your PhD is already completed. So if you just focus only on this half slide, and you really understand that, then I assure you, then you have a very bright future. And the reason behind that is it's one of the hard topic these days. Polymer membrane synthesis, that's a topic over there. Now, if you are afraid of that in a membrane, there is some complex chemistry, and that complex chemistry, because their membrane must be made of some organic compounds, and I don't want to just discuss that kind of issues, then you have another option as well. You have ceramic material. So ceramics material are quite easy. That is why whenever I just started this class, uh, from the very beginning, I just addressed that issue that material synthesis is the most important one for any research student. So ceramic material, now how to prepare that? That's also quite easy. For that, you don't need a very high sophisticated instrument. Of course, we need for characterization some instrument, but for synthesis, we don't need that. For synthesis, you have different kind of synthesis. You can prepare in the crucible. You need a crucible, which is a high temperature absorbable instrument. Glassware, sorry, is not an instrument. And then you need a furnace. And these two things are available in every lab. So you can also prepare that. And you can also then check that ceramic, that either what's about this property and this one, that either it's electronic insulator or not, either it's a good ionic conductor or not. If you can do that, if you can prepare that, is okay, you have achieved your goals. Then you check that either it is stable in oxidizing condition or reducing condition or not stable. Then you can also have that kind of side waves. So from this particular, even a one segment, you have very broader views. Now you can extend it. You can go and browse your internet just by membrane for fuel cell, ceramics for fuel cell. The different people have different approaches. So you can also reproduce the same material by another way, or you can produce a novel material. So that is a one kind of study that you can conduct. What else is most important one? Now a negative fuel cell electrode. And that negative fuel cell electrode, it seems to be a simple electrode, but that's not a simple electrode, keep in mind. Now, basically, there are different things, they are mixed together. And in the previous discussion, in the previous class, I told you that we have one part synthesis. In that one part synthesis, we preparing some material. And that is a material of our interest, or simply that is our catalyst. So let's suppose you had prepared your catalyst, and that catalyst is a platinum based or platinum free catalyst. So let's suppose it's a platinum free catalyst. Let's suppose that is nickel. Okay, you had prepared nickel, and that nickel is of the size of 10 nanometer. Now you cannot use that nickel as such in the electrode, negative fuel electrode. What you have to do, you have to load on the carbon, and in that I have teach you last time that how to load on the carbon. You have to take activated carbon, and that activated carbon you have to sonicate. In the sonicator for 20 to 30 minutes, and then after that you have to add that nickel slowly and gradually drop wise in that activated carbon, and then sonicate again. And then if you take the TEM image, you will see that there must be a fine dispersion of that nickel on that carbon material. Now then we are coating that carbon material on the electrode surface, and we are using that electrode. So now you can see that incorporate electrocatalyst. Now what's our electrocatalyst? I told you that nickel is our, in the particular specific example, which is dispersed on electronically conducting material. Now what's conducting material is our plates. That I told you that we have a negative plate, a positive plate, so we have this that. And that electrode is fabricated so that electrocatalyst, electrolyte, and the fuel in the simultaneous contact. Now that's very important. Okay, that is your material. Sorry, that is your electrode now. Now you know that this electrode is not a simple now, because there is electrocatalyst, and that electrocatalyst that you have incorporated your active material on the carbon, finally disperse that, and then you have pasted it over here. Now the electrode is fabricated so that electrocatalyst. An electrocatalyst, I told you in your case, you have, let's suppose nickel. I'm not sure that nickel can be a best catalyst, but it's just randomly, arbitrarily come in my mind, so I had used over here. And electrolyte. Now electrolyte, because there is some material between these, if that is a negative plate and that is a positive one, so there are some material over there also. Okay, Sorry, that is a negative. Okay. And then fuel. Now the fuel is coming on this side. Let's suppose that is a hydrogen. Okay. So electrocatalyst, and then our this medium, and then the fuel. All of them are in contact simultaneously to that one point contact, and that is why we call them triple point junction. Okay, that's the term. Triple point junction are three phase boundaries. Now I think it's very clear. It must be the same for positive fuel cell electrode. The second point you should keep in mind here, the term is negative fuel electrode. Why they had used this term? It's electrode. There's no doubt in that. It's electrode or not, it is electrode. It's negative electrode, it's also clear. So it's fuel electrode. Why we call them fuel? Because it takes hydrogen, and that hydrogen is splitting into H positive and they give electron. That electron is passed through this material to external circuit. So that is why this is a negative. Now the reaction happening over here is this one. And this reaction is called hydrogen oxidation reaction, HOR reaction. Hydrogen oxidation reaction, because electron is going to remove from this species and the oxidation state is going to increase. So we call them hydrogen oxidation reaction. Okay. Now here, again, you have another perspective on the research side. You have a research perspective. That you can go and browse your internet and you can find out on the Google Scholar, on the Science Direct, on any scientific community, you can go and find out that there are different publications of different researchers that they have fabricated with different metals. Because initially we are using platinum, and platinum is one of the best catalysts because it can do that HOR reaction at 0.000 volt. And I'm sure that you remember that. But we know the cost of platinum is very high. And due to its high cost, that's a hindrance in just use at large scale. That's a big problem over there. And there's just elevation in the price. So we can replace that platinum. You can replace by some other material as well. Now, why this platinum show so high activity for HOR reaction? That's a big question. Why platinum shows such high activity for HOR? Why? What's the reason? Now, if you really understand this question, then there's an opening, a new chapter open for you in the research side, that you can easily handle that, and you can easily continue your project just by designing that. That's a one question. Now, if you really understand that basically due to its electronic arrangement, that the atoms, they are arranged on the platinum in such a fashion that the space between them is suitable for hydrogen adsorption. Now we need such a catalyst that do not need to attach the hydrogen strong enough to do not leave it. So then we need an optimum time for that attachment. Then we can play with other material electronic structure just by doping or just by alloying and just by making different sort of geometric shape which can change its electronic arrangement, and they make it favorable for this HOR reaction. Okay, so that's very important for fuel cell. Now what else? A positive electrode. Now positive electrode is also a triple point electrocatalyst. Now you understand that triple point electrocatalyst, because here there is also we have some electrochemically or electrocatalyst or electroactive material, and we have already electrolyte over there, and we have already some oxidant. Now in the previous case, they say in the negative fuel cell, we have here fuel come in contact. But in the positive electrode, we have oxidant. And that oxidant, like Francis Bacon, according to his experiment, he just used oxygen vapor. But you can also use air. Okay, of course, there must be some complication whenever you are switching from oxygen to the air, but you can use it. Okay, that is incoming oxygen either alone or in air. The second point you should keep in mind that I told you that platinum is the one of the worst catalyst for that ORR reaction, oxygen reduction reaction. That oxygen in the molecular form is going to split into its ionic form. That's called ORR reaction that I will show you just sooner after a few slides. So then you have to replace this platinum by other metals, and then you can check its activity. So sometimes we are conducting some experiments that we are preparing a material for negative fuel cell electrode, and we are also checking its activity for positive electrode. So whenever a material that we are going to deposit on the negative fuel cell electrode, and then we had deposited on the positive fuel cell electrode, its activity is good enough or comparable to the platinum and the negative fuel cell, and also good enough on the positive, we call them bifunctional catalyst. That you should. That is bifunctional catalyst. Okay. So that's very interesting that if you are able to prepare some material that can be used for fuel electrode, and they can be used for oxidant electrode as well. So these are different research perspectives that you should keep in mind. The third one is a bipolar plate. And this basically you should remember that the fuel cell the output is very low. Okay, so when the output is very low, then what we should do, so we should have to build up the high voltage or desired voltage just by uh, electrically connecting cells in series to form stacks. And when we connected in the stacks, this is only achieved by a bipolar plate and frames arrangement. Now you should keep in mind that if we have just, that is one cell, that is another cell, and that is the third one, and that is the fourth one, and we are just connecting all of them in series, there must be a bipolar plate between them. Okay, now the function is to connect individual cells together. Okay, the second one, it should have some channels that if we are passing gas through it, because we are using fuel, so on one side they must pass a fuel, so they must be modeled in such a way that they can pass gas channels. Okay, the second one, they have also facilities of water coolant that we can also pass water through it or air through it in order to make the whole arrangement or cell stack cooler to perform in a better way. So they have both the facilities. The first one is for circulation of water and for circulation of gases as well. Okay. But again, here we need a pure water for circulation, particularly in case of hydrogen fuel. Now, this is why we need this. If we don't use this pure water, so it causes corrosion, and that corrosion must lead to the ultimate decrease in the efficiency of our fuel cells. So that is also very important, a bipolar plate. Okay, then we need a seals that keep gases apart and also prevent cell to cell seepage. Okay, liquid electrolyte. For individual cells, no problem, but for if you are just making a cell stack, then of course if there is a leakage on one side, so that may cause short circuit. Why it causes short circuit? You should keep in mind that the material that we are using between the two plates, basically they have the ability to conduct electricity, and they are conduct electricity not in the form that they can conduct electron, but they can conduct ions. So whenever they are conducting ions, so that ionic conductivity is just the conduction of electricity, and they can cause a short circuit and just damage our cells. Okay, then we need a current collector, and that current collectors, they are located at the ends of stacks. Okay, basically they are collecting the whole current. They are being generated from different cells, and on one side of the cell stack and another side of the cell stack there is a current collector. There's also another research topic on this sides, that how we can improve the ionic the electric conductivity of this material very high, and they have a high resistivity toward corrosion and degradation, and they have high thermal stability. So there are different materials and alloys. So these are purely material side research sites. The other one there that's most important that this is also a requirement for the fuel cells, that you should also have some arrangement or requirement for what circulation of water through it. And that circulation of water is a cooling, for cooling purposes, that is heat removing, because there is a continuous heat accumulation due to that chemical reaction, and that accumulation of heat may damage some part of the cell, or they can damage or they can decrease the activity. So that is why you need to circulate water through it, and you need a pure water for that circulation as well. So that's also very important. Okay, so till now what we have studied, basically we have studied just a few points till now, and these points you can see here. That's what's electrolytic medium, and I told you electrolytic medium may be acid, may be base, or it may be a membrane, or maybe a ceramics. So you have 8 research topics now in your mind. We have negative fuel electrodes, and I told you basically we are using platinum. You can replace. We have positive material you are going to search is a blank for you. A bipolar plate, and I told you what is the function of bipolar plates. We have seals, we have current collectors, and we have requirement for air liquid, air or liquid coolings. So that we are the basic requirement for our fuel cells. Okay, so these are the essential element for any fuel cell. And we also need to stack a lot of fuel cell together, and then we can get a desired output from that fuel cells. Okay, now it's a little bit historical point of view regarding fuel cell. Uh, and here, as I told you, that the pioneer in the fuel cell was Sir William Groove, and that was 1839. But from 1839 till 1946, there was little attention given to that fuel cell, and that's the reason that Francis Bacon, for the first, not for the first time, but after William Groove, he worked on the fuel cell in that 1946 to 55 at University of Cambridge, and then Marshall of Cambridge Limited from 1956 to 1961. So combining the whole time that he given over here, 9 years, and then 56 to 61, 5 years, almost 14 years, his work with interest in the fuel cells back to 19. Basically, he was an engineer, and he selected alkaline fuel cell. And being as an engineer, he appreciated the potential advantages of the fuel cell over both internal combustion engine and steam turbine as a source of electrical power. Now, basically, he selected alkaline fuel cell for his study, but he restricted himself to the use of pure hydrogen and oxygen reactant. He never think about the other thing, and he was very focused and very determined to his study. Now, later on in his recognition to the outstanding contribution, he was elected for the Fellowship of Royal Society in 1991, and he was the first recipient of Groove Memorial Award by the Groove Fuel Cell Symposium. Now, here, alkaline fuel cell, basically he used a nickel-based electrodes. As I told you that platinum was very expensive, and there's also shortage of platinum as well. And at that moment, Francis Bacon was sure that it's impossible that platinum can be commercialized in the fuel cell. So that is why he just worked most of his time on that alkaline fuel cell, but that was a nickel-based alkaline fuel cell. Now later on, that what he had done in the USA, fuel cell was first used to provide spacecraft power during the 5th mission of the Project Gemini. The success of the fuel cell in the space program stimulated that it may develop. There must be some development in addition to that spaceship for terrestrial application as well. But for the convenience and economic values, if we just look at the economic, that dictates that on Earth it's generally necessary to use air rather than pure oxygen for a positive electrode reactant, and this introduces some technical challenges to the fuel cell. So that was just a little bit about the history. Now there are advantages, not little advantages. There are many, a dozen of advantages of the fuel cell. And what are these advantages? Basically, it have a lot of advantages over generators and electrical for electrical energy, such as turbines, gas turbine, steam turbine, or internal combustion engine. Now, we can just count here some of the few advantages of the fuel cell. Potentially, it have high energy efficiency. And whenever we are talking about efficiency, so in the internal combustion engine, there are a lot of moving parts and a lot of mechanical energy is being lost and some heat is being lost during that mechanical energy and heat energy. So we can hardly get 30% efficiency. What about in fuel cell? Just we can just consider as theoretically, if we just take it into account, we don't keep in mind that is the T delta S heat. So it's almost 100% efficient fuel cell because there is no loss, there is no environment toxic chemicals. So it's 100% environment friendly. So potentially it have higher efficiency as compared to that of a steam turbine or that of internal combustion engine or any other engines. Now, greater efficiency when operated at part load in contrast to engine. Now, there's also very important in most of the cases, if we just compare the size and mass of the fuel cell and mass of the internal combustion engine, there is no proportion at all. And later on, I will just discuss that if we compare a 100 kilowatt source internal combustion engine or turbine, so the weight is almost 500 to 5,000 times greater than that of fuel cells. So that's also important. And there is no moving part and no moving component in the fuel cell. They don't have any fans, any blowers like that, and they need a little lubricant because we have just electrodes, we have a medium, and that medium we can use any membrane or liquids or whatever the case may be, but we are just using that, and there is no moving part. So when there is no moving part, we don't need lubricants for that. So on the one side, there is no enough amount of, there is no heat emission in the fuel cell. And the second point, the cost of that lubrication is also being saved. So the fuel cell is more attractive, almost silent. Now, if you just compare the turbine, internal combustion engine, steam engines, and the fuel cell, now we know that the fuel cell is quite silent. There is only chemical reaction over there and no other moving parts. So it's very silent and they don't create any sort of sound pollution or noise pollution. Okay, and flexibility of fuel supply. You can use hydrogen, maybe derived from many primary fuels. You can use hydrogen carrier fuel cell. And hydrogen carrier fuel cell, there are a lot of examples. Any hydrocarbon you can use over there. So there is a flexibility of fuel supply. You can use any fuel over there. Of course, there must be some necessity for that you should also adopt some what about the residue beyond that hydrogen, how we can tackle that and how we can just treat that. That's another issue, but just for the sake of fuels, we can use any fuel over there that contain hydrogen, because the basic reaction that you should take hydrogen over there is positive. Now, any fuel part, let's suppose that is A part, anything, so that you just detach this hydrogen from there and the electron may go outside through external circuit. So that's the basic phenomena and the basic principle over there, okay? And virtually, as I told you, that virtually there is no exhaust pollutant. The only product that, a byproduct that we get is water, and water is not a pollutant at all. So there is low environmental impact and suitable for indoor use. It's so safe that even inside a compound, you can also use a residential area, you can use it without any danger. So fuel cell is very important in that case. Now, the pure water emitted when you use hydrogen as a fuel cell, that you can use for lab purposes, that you can use for any other purposes, because that is a triple distilled water. It is a distilled water. Okay, so whenever you get this kind of distilled water, so at a time you are using hydrogen for fuel, and on other side you have also, there also work as a distillation plant. So that's very interesting. There is a rapid load following response time. As long as you are supplying the fuels, you can get a response after preheating. Of course, you need to heat your fuel cell before operation. So some fuel cell, they work at 200 degrees centigrade, some at 50 degrees centigrade, and there are a range of temperature on which it can work. So, but the response, they are quite fast. There is a rapid response. Now, a good power to weight ratio. So that I have discussed before, that if you just compare, there is a very simple comparison between two kind of combustion engines. Like I have a data that if you are taking 100 to 1000 to 2000 megawatt capacity, any turbine or internal combustion engine, so is somehow 500 to 5000 times larger than fuel cell. You should just keep in mind that is a ratio. If you have a 1000 to 2000 megawatt capacity. So what do you think about its combustion engine or turbine? So it's almost, that's not exact 500 to 5000 times larger than fuel cells. And that was the reason that in the spaceship programs, they have selected fuel cell because of this issue. That was the major advantages of the fuel cell. They do not just cover a lot of place over there. So that's really very important. Okay, that its modular construction is very easy. There is nothing confusion at all. Even the basic chemist can also design that, and they can give you a high efficiency, and ease of installation is also very easy. Okay, now that's very important that against these advantages, there are some difficulties over there in the refinement of fuel cell. Because I told you that whenever you are fueling natural gas or any other hydrocarbons, so first you need to reform that to hydrogen or methanol and then purify it. So they make the task more difficult, and these are the other hurdles that you can face while using a fuel other than hydrogen. So first you should have to refine that. So there are some problems. So there are no free meals in the world. So of course there must be some problems. They are integrating with that, and then you can then you can just use it as a fuel. Now, in terms of kinetics and thermal management, the two different systems. The first is a refining system, and then the fuel stakes. Then it becomes a hybrid system. Then that hybrid system, the kinetics and the thermal management, they become a little bit difficult. But that doesn't mean that's not easy. That's not possible. It's quite possible, but still it's a little bit difficult. Okay, so now the potential use of fuel cell are extremely diverse. That later on we will discuss it in this presentation, that there are the spectra of applications of the fuel cell is ranging from heavy duty trucks to the small cell phones, laptops, cameras, and some like that. But on that basis, broadly application fall in three categories: the stationary categories, and the second transportation, and third portable. In the stationary, as the word indicates, stationary means that it should be stable and it's not moving. So disperse electricity generation at the local level up to several megawatts. They can create several megawatts. Combine heat and power, that's one of the best attractive project, that you can combine heat and power for residential and commercial premises, hotels, hospitals, emergency power suppliers, and remote areas you can use for stationary. For transportation, it can be used for cars, trucks, and buses, railway locomotives, submarines, and subsea vehicles as well. For portable, for laptop, computers, mobile phones, and personal digital assistance. Okay, for military equipments, also for communication devices and global positioning, that is navigation system, receiver, portable radio transmitters, and there are so many other applications. You can read that. Okay, now the basic difference is between stationary. Okay, among stationary, that is we have a stationary fuel cells, and we have for transportation applications, and the third one, that is a portable one, portable electronic. That's three. Now the stationary fuel cell, that range is important, that you should keep in mind. That is 1 kilowatt to multi megawatt power range. For transportation, this application may stretch from few hundred watt, let's say electric scooter, to a multi-watt. Okay, and for portable, it's obviously 1 to 100 watts. So that range is important, that you should keep in mind, that whenever we are discussing any fuel cell and we need to use it for stationary fuel cell for stationary purposes, of course we must have to stack a lot of fuel cell together, and then we can use that. Otherwise, if we are using for electronic purposes, so a few may be possible. So that's very important. Then there are different type of fuel cells. Okay, and that fuel cells, keep in mind the fuel cell. Okay, that is if you just take the voltage is plotted versus current density, and the current start to be drawn as the voltage falls. This impact that the contribution loss in performance are reflected at different regions of the voltage current curve. So if you take, okay, that I may discuss later on, but here there are different type of fuel cells. Now you can easily understand that phosphoric acid fuel cell, alkaline fuel cell, direct borohydrate fuel cell, proton exchange membrane fuel cell, and direct methanol fuel cell, and miniature fuel cell. But these are, all of them are used at low to medium temperature. Okay, low temperature or medium, and we have also some high temperature fuel cell as well, like molten carbonate fuel cell, direct carbon fuel cell, and solid oxide fuel cell. So these are three are here, and in the previous slide we have 1, 2, 3, 4, 5, and 6. So we have total almost 9 kind of fuel cell in this presentation, which of course is not possible to cover all of them, the detail of all of them, but I will just give a touch to some of the fuel cell. For example, I'm just taking the first one as a phosphoric acid fuel cell. And I will try to discuss some of the details, not all of the details, because all of the details are not possible to discuss here in this presentation. So then I will just give you the some data and some papers from where you can easily read that, and some books that are published by the Royal Chemical Society, Hydrogen Challenges and Perspectives. There are some books, so there are some chapters of that book that are completely devoted to only that fuel cell, and you can go through that material and study that, and that's really very interesting. Okay, the first one is a phosphoric fuel acid fuel cell. Here you have the idea now from that general concept that a fuel cell is composed of electrodes, a medium, fuels, and oxidants. Now here, where we can use phosphoric acid fuel cell, is it possible you can use as a fuel? So no, as a fuel is not possible. We can use as an oxidant? No, of course it's not possible to use as an oxidant. So where we can use it, it is used inside the compartment between cathode and anode. So phosphoric acid solution is electrolyte are called phosphoric. We are using that as electrolyte in between cathode and anode. Okay, because there is a reaction of that is phosphoric acid is converted into, that give us a proton, and basically we need that kind of thing that facilitate the water productions. So solution they dissociate into phosphate ions and hydrogen ions. Okay, phosphoric is chemically stable, and that's easy to handle. It's also extremely low vapor pressure, even at an operating temperature of 200 degrees centigrade. So it's quite easy that what's the operating temperature of phosphoric acid fuel cell. So it's 200 degrees centigrade. That's the operating temperature. This implies that phosphoric acid in the electrolyte layer cannot be easily discharged from the fuel cell together with the cell exhaust. Okay, so it cannot go outside with the cell exhaust. Although even at such a minute discharge, they result degradation of performance in long term. For example, if you are using a cell for long term for 1000 cycles or 2000 cycles or 3000 cycles, then of course it may count. But for short time is of no problem. Okay, now what is the basic structure of phosphoric acid fuel cell? Now keep in mind, last time I told you that basically this material, that is our electrodic material, a negative plate, that's not as it look like a rod. That's not a rod. Okay, so basically it's made of different materials, like it's a silicon carbide and carbon, and then we are adding also polytetrafluoroethylene and that is polytetrafluoroethylene. They are used together, all of them, and then this fake formation also occurs. Now keep in mind that this material and this, they also contain platinum, and that platinum is used in such a fashion that the surface area of that platinum is equal to 100 meters square per gram. Now, how it is possible that we can increase the surface area of the platinum? So you have a clue, and you have already studied that. If we want to increase the surface area of any material, we are going to decrease its size. So if you are able to decrease the size of that material, that's great, and that's the reason that this size is achieved by preparing a platinum of 2 nanometer range. So 2 nanometer range platinum, and then they are platinum are loaded on the carbon loaded platinum. That's 2 nanometer, have a surface area of 100 meters square. And then they used here 0.1 milligram per centimeter square of the material. And on this side, 0.5 milligram per centimeter square. And you know the reason that why we are using on this plate 0.1 and why we are using 0.5. You know the answer why. Okay, then cooling for large scale, that's also mandatory, because you know that if you are using only a single cell, what will happen there? The chemical reaction happening on this, that is a fuel cell electrode reaction. Okay, and here hydrogen is going to split into proton and they give a 2 electron. Now these 2 electron is going to move in this way, in this direction. Now if you put anything here, it will start like this. Okay, and then when they reach here, so their dotted structure here, you can see that it's represented by electron. Their dotted come here, and this one is the oxygen. Oxygen combine with it, and when it combine with oxygen, they form O negative, and that O negative, and then combine with this hydrogen ion, that is a proton, and they can give us a water as a product, and the water is represented here, come out over there. So here there is a production of these holes. This hole is nothing but these are the hydrogen ion or proton. Okay, and on this plate these holes are coming and they are attached here. Now what happened at air electrode? This is the reaction happened at air electrode. That is oxygen and that is hydrogen coming from other sides. They combine together and then electron and they give us a water. So what will be the overall reaction? So we know that the overall reaction is only the simple one. Okay, so but under normal condition, it gave us it is 0.6 to 0.8 volt. It's not enough. So what we have to do? The second point over here, that you need a pure water. So if it gives us a so low voltage, then we have to stack. That is, if there is a one cell, we have to take another one, we have to take another one, and so on, and we have to combine so many of them, a dozen of them in series, like here, and we can make stack of that fuel cells, and they can be used. But here there must be a separator, and that separator, you can see that the top one and this one, you can see here, This must have functions like that we had already discussed in bipolar plates. That's nothing but that bipolar plates. They have also a facility for that air channels. Air can easily circulate through that, and water can also circulate through. Now, why air? Basically, the fuel maybe just if you are just supplying hydrogen, they must have a channel for that. And the other one, if you are supplying some oxidant, they also have a channel for that. If you want to circulate water through that, they also have that facilities. So that is why we are using this fuel cell in the form of that stakes in such a fashion. The second point, that if you just take the efficiency, so efficiency of that fuel cell is 40 to 50%. It seems to be quite low, but keep in mind that it doesn't mean that kind of efficiency which is generally used. Here by efficiency, we means the ratio of electrical energy generated by the cell to the hydrogen energy consumed. Okay, if the waste heat generated can put into good use, then efficiency may be increased to 80%, which is very high efficient. Okay, and the other thing that I just remind you, that if you take the mass and the size, so it do not cover a lot of space, so that is why it's much more efficient. And I told you that if you just compare 1000 megawatt capacity fuel cell, it's almost 5000 times smaller than that of a turbine or steam turbine or internal combustion engines. So that's the basic differences over there. Now, okay, this is one of the power plant, that is PAFC, and phosphoric acid fuel cell, and it can generate 200 kilowatts of power. So that is why it's, and I just remind you one thing that's really very important, that you don't need to forget that here it's given it's a fuel cell, so the output power, it's rated by the power that is measured in watts. If it was batteries, then we just compare in ampere hour, because that is the capacity. So here you can see here now the power plant. So there are some practical, and keep in mind that was the first commercialized fuel cell, and that first commercialized fuel cell was phosphoric acid fuel cell. So there was some information regarding that. Okay. Now, the second one was alkaline fuel cell. And alkaline fuel cell started by Francis Bacon studies. And I told you the usual procedure. There are to prepare alkaline fuel cell, that is quite easy. They must contain a electrode as a cathode, electrode as an anode, and then after cathode and anode formation, uh, the medium between them must not be phosphoric acid. As the electrolyte in the bake phosphoric acid fuel cell was used the phosphoric acid, but in alkaline fuel cell we are going to use uh, only alkalis, and that alkalis may be potassium hydroxide and sodium hydroxides. And that is the study of work of Francis Bacon at Cambridge, and then another technology, some industries. Now, pure oxygen rather than air serve as an oxidant in alkaline fuels, and that we have discussed that they need pure oxygen. That's not very important to, they need pure oxygen, but in most of the cases in space programs they use pure oxygens. And why they use that? In order to minimize the mass of the gas cylinder. That's very important. And for the simplicity of the system. For most terrestrial application, now consideration of cost, that is important, and portability rule out the use of oxygen. So you have to use a mixed air, and that mixed air creates some technical problems. And what are these technical problems? They are susceptible for poisoning of the catalyst due to carbon dioxide and carbon monoxide. Now, how to remove that and how to rule out that? And that's a very straightforward reaction, because they are combining with potassium hydroxide and forming potassium carbonate. So that potassium carbonate is just the degradation of our cell performance through a variety of effects. Now, the usual procedure to pass these gases through the soda lime trap has to be replenished from time to time. This operational is inconvenience rather than the fundamental obstacle. For a similar reason, hydrogen fuel cell must completely be free of carbon dioxide. In addition to carbon monoxide, we don't need carbon monoxide and carbon dioxide because these are the reason that can decrease the performance of our cell, and that's a declination point. So now, in order to remove that things from our fuels and to remove from our electrolyte and from the oxidant, so that necessitates rigorous cleaning and the separation of the gases, and they impose the additional cost penalty. So the cost is going to increase. Now, for this alkaline fuel cell, keep in mind the normal nominal operating temperature is 60 to 90 degrees centigrade. And that's very interesting that its operational temperature is 60 to 90. The previous one, if you remember, that was 200 degrees centigrade. So it's just a much lower temperature than the previous one. Now, it doesn't mean that it do not work above 90 and below 60. It can work, although it perform over a wide range of temperature. Like it can work at 50 degree and it can work above 90 up to 150 degree. Now it's according to your choice of gas pressure, your electrolyte concentration, electrocatalyst. So it is possible that it can operate even at a higher temperature. For example, the Apollo spacecraft program, they had used at 230 degrees centigrade. Now 90 and 230, there's a big difference. But what they had done for that, basically they increased the concentration of potassium hydroxide from 30 to 75% weight. So he had used at 230 degrees centigrade, and what he had done, the increase in the concentration of that potassium hydroxide, and that is from 30 to 75%. Okay, and why he had done this? In order to prevent boiling. Now, giving a relatively low operating temperature of alkaline fuel cell, little heating is required to start up. As we know that this is a nominal temperature, operating temperature, so it don't need a lot of heat to give to the system. So, which is very rapid. So this picture provide alkaline fuel cell with the testing advantages. And there are different industries they used to prepare. For example, Elenco was an industry, they prepared alkaline fuel cell up to a multi-kilowatt, the power of for electric vehicles, and they work at a temperature from 65 degree to 70 degrees centigrade. And they used to circulate potassium hydroxide with a concentration of 6.6 molar, and the function of that is both as a coolant and as a preheating medium. Okay, so and they stake together 25 cells assembly in series, and they use a platinum, and that platinum they had used on 0.15 to 0.3 milligram per centimeter square, and they give us a current density of 100 milliampere per centimeter square at a 0.7 volt. So that was just the data that how they had constructed that, and the system output was 1.5, 15, 50, and 80 kilowatt. And they also arranged an electric vane, and that electric vane was for 80 passengers. But later on, they just understand due to that problem, and that's just, I told you that carbon dioxide poisoning, it's a big issue. So due to that issue, they have just stopped that. And then later on, after the mid of 90s, Elneco just discontinued manufacturing of fuel cells business, and they stopped that. So now what's in the alkali fuel cell? Basically, decrease in the concentration of hydroxide ions lowers the rate of reaction at negative electrodes. The second one is reduction in the solubility of oxygen, which intensify activation losses at the positive electrodes. These are some hurdles that you can see here. Increase in the viscosity of electrolyte, which result in lower diffusion rate. For example, if you are going to increase the concentration, now increase in the concentration may lead to some other factors. And what are these other factors? The first one, that lower the rate of reactions. And you know why, whenever we are increasing the concentration of any material, why it's lower the rate of chemical reaction? Because there is a competition of moving a particle toward the material in order to cross that inner Helmholtz flame, outer Helmholtz to the inner Helmholtz flame. And if you remember that 7-step mechanism, that a material, if there is any species coming from a solution, from the bulk to the surface, and then activation state, then attachment, then electron transfer, then deactivation, then deionization, and then coming back. So the holes, they are considered as a kinetic. So the rate is basically decline because of that intensifying concentration. And they also increases the viscosity that result lower diffusion rate of the reactants, because if you are increasing the number of particles per unit volume, so of course their diffusion must be very slow as compared to that. That's not in the gaseous form. I'm just talking about the solution form. So in case of a solution, particularly to electrochemistry, that if you are increasing the number of ions per unit volume, then there is a competition. So you are not increasing only a positive particle, you are all, at the same time you are increasing the negative one. So there must be an integration between them. Now a fall in electrolytic conductivity, and that's, you know, that whenever we are decreasing the concentration, then there is an increase in the conduction. And there are two reasons for that. The first one, that every particles can move freely and there is no ohmic loss, and that you have studied in your basic electrochemistry. Now there is also a precipitation of that is the eventual precipitation of carbonate, which is capable of deactivating the electrodes and blocking of the force of an M-mobilized electrolyte or the pathway of the circulating. So the whole circulating channel may be blocked by this precipitation. So on one side, if you want to use that at a higher temperature, and we are going to increase the concentration of potassium hydroxide, so they also lead there are a lot of consequences of that cells that procedure. So it's therefore essential to treat the air to remove the carbon dioxide. That's very important. Okay, so in summary, alkaline fuel cell based on pure oxygen have been proved to be the powerful and successful, whereas operating in air appears not to have a commercial future at present. Sensitivity of alkaline electrolyte solution to carbon dioxide is the principal reason. That's the reason that since 1970 there is not much improvement in that. So that's the reason that why till now we don't see any sort of commercially available alkaline fuel cell, although in 1970s they have used in their space mission. But later on we don't see on terrestrial level for terrestrial purposes. And the reason behind that, I told you that the only reason, that is the sensitivity of alkaline electrolyte solution to a carbon dioxide, is a principal reasons. Now, if you are able to prepare such a assembly in which you can block carbon dioxide, or you can just prepare some CO2 repellent inside that medium, that may be the great idea. And still the window is open for any of the research students, that they can do any research just by blocking that carbon dioxide. There are some other ways also, and researchers have just tried to find out there are some other ways for their purposes. But still we have a long way to go. So that's the reason that there are some advantages and some disadvantages at them simultaneously. Okay, we have another kind of cells, we call them direct borohydride fuel cells. I'm not sure that previously you have heard about this kind of fuel cell or not, but that's really very interesting at this level. Now you can see here sodium borohydride. And sodium borohydride is unstable in acidic medium, okay, but dissolved in a strong alkali to yield a stable electrolyte solution. Okay, so if you just understand only the first line, then you understand the whole scenario of this DBFC. You should also sometimes try to remember that abbreviation as well, because whenever we are going to compare the activities, selectivities, operational time, and yield of the different fuel cell, so we will just use only these abbreviations. Okay, so sodium borohydride is unstable in acidic media but dissolved in a strong alkali. Okay, so now this then is a variant of AFC, alkaline fuel cell. Okay, with the added attraction that is not necessary to provide a cylinder to compress hydrogen. And that's very important, that it simply means that at the same time you are also producing some hydrogen now, so you don't need to compress the hydrogen rather than the fuels. It's already present in the electrolyte solution. Already your fuel is already present inside the electrolytic solution. So the discharge product is sodium borate, NaBO2, which if desired could be factory recycled. That may be possible that you can recycle that. Now there are some limited research on this system, uh, and the reason behind that is why there is a limited research, because it's not according to the which is the basic scheme of that fuel cell. So there is some limited research on that. At least one Japanese company, they are developing this. And why they are doing this? Because there is a direct methanol fuel cell. They want to find out alternative of that as a power source. And for what? Basically for computers, laptop, and possibly for mobile phones. Thus, the direct borohydride fuel cell is a certain characteristic of alkali fuel cell, or are strongly alkaline electrolyte, or other direct methanol chemically bound hydrogen, and suitably to power portable electronic devices. So on one side there is not too much research on that, but on other side commercially still there is a one industry, they are continuously working on that and they are preparing that, and maybe it can be a best, not a best, as a one of the competitor in that electronic industry. Okay, there is the most attractive one and the widely studied. It is proton exchange membrane fuel cell. This is also called polymer electrolyte membrane. So polymer electrolyte membrane fuel cell or proton exchange membrane fuel cell, the abbreviation remain the same. And as a solid polymer electrolyte fuel cell. Now here, this point that I have discussed in the start, that now we are switching from medium, solution medium, toward a solid medium. Previously, we had used a solution, acidic solution, and we call them phosphoric acid fuel cell. Basic solution, alkaline fuel cell. And then before this, sodium boro, that is borohydride fuel cells. So that was the third one. And now we are shifting from all these towards a new scenario, that is a solid polymer membrane. So that is very interesting. This membrane, what's the function of that membrane? Now keep in mind that it is an acid electrolyte fuel cell that operate at the same principle as phosphoric acid fuel cell, although there are some important differences. And what are these important differences that we will go to discuss one by one, slowly and gradually, and it's very interesting amongst all. The electrolyte is a thin membrane of a copolymer. Now, polymerization, there is a copolymer, and what's meant by copolymer, I'm sure that you remember that what's meant by copolymerization. So, electrolyte is a thin membrane of copolymer, and that is highly conductive to hydrated proton. The standard membrane material is sold under the trade name of nephines, which is produced by DuPont Corporation in the USA, original application for some alkali industries, chloralkali industries. So here, the backbone consists of PTFE, and that is polytetrafluoroethylene that we had discussed before. That is the backbone, consists of this. And to a side change of the perfluorinated vinyl polyether is bonded with oxygen. Now there is some modification with the basic one. Sulfonic acid group, that is SO3H, at one end sides, they can exchange with the proton to facilitate the passage. Now this must have two characteristics. One is a water repelling characteristic, and the second is a water absorbing characteristic. And you will astonish that how it is possible that some of the compound have both the qualities at the same time. The first one, you can see that PTE, polytetrafluoroethylene, is the backbone, that is a water repellent. Because it's organic compound, so it's a water repellent, no doubt in that. And that prevent flooding by product water. If the water is going to produce, they are going to repel the water. The second point, that there is sulfonic group, and that sulfonic group attract water molecules that from aqueous micelle within the polymers, and these intrude serve to conduct the protons across the membrane. Now, so that's another advantage. So these two characteristics, they are very astonishing. Now, the perfluorosulfonic acid membrane as a class have inherent chemical and oxidative stabilities. So they have a chemical and they are chemically stable. They are, if there is any oxidation reaction, they again are stable. They are also working as a prevention for flooding, and they are also attracting water for conduction of protons. So they have a lot of good qualities as well, and they are however difficult to manufacture. Now that is again, as I told you, that it's not easy to prepare some kinds of things which is beneficial for us, and we can prepare it with ease. It's really very hard sometimes, but still, it's also expensive. But it's not impossible. According to the companies of USA and some Japanese companies, searching for significantly cheaper alternatives. So that is an open choice for any research students, that the nephine membrane, which is expensive and which is hard to prepare, if you are going to find out alternative of that. And whenever you know the characteristic properties, that what is the main purpose why we are using that inside a fuel cell, if you understand that, and then you know that what are the problems relating to that, then it's really very easy to work on that. So the point that why we are using, because handling a liquids fuel cell is really very hard. Membrane fuel cell is easy to handle. That's the first advantage, is that even we can convince a layman. The second point, that there is a water that is going to produce at the end of a chemical reaction. So water preparation is the second point. Now, when you take both of these components together, that is, there is water inside a fuel cell, and so we need a repellent. That is a wiper. They can clean the water from there. The second point over there is also some proton. So we need a proton to exchange from that negative electrode toward the positive one in order to get the water. How to do that? So if we can prepare any of the membrane which is cheaper than the nephine membrane and which can easily be prepared, then that's really a wonderful work. Now most of the researchers, they are working on that development of thinner membrane. Then if they can attain, there must be some the benefits must be electrical resistance and high power density and improved hydration. So all the qualities of the new open research field, you know about that. Now what we need, basically we need a little thinking about that, a little work about that, and then of course it's not hard to prepare. uh, and then there must be a breakthrough in the polymer exchange membrane fuel cell or proton exchange membrane fuel cells. Now the basic assembly of that cell is given over here. Basically what's here is scrubby material on one side, and there is also some scrubby material on another side. So one is our fuel electrode, and the second is our carbon electrode. And here it's very clear that it's a carbon cloth. Okay, so we need some space. As I told you before, we need some spaces between these materials. So it's very easy for us that hydrogen can penetrate through that. And we also need, if that is the black one is the carbon, so we also need, you can see here there are some kind of attachment, that white color in this figure. You can see here that there is some platinum also. Okay, so basically this platinum is a catalyst, and the reaction that must happen at the interface of at the surface of that platinum, so it must be exposed. But how the hydrogen can come in contact with that platinum, so we need some channel work, and some channels, and that channel is basically from there due to that carbon. On other sides, we also need oxygen, and you also see here oxygen come in contact with that of material. Now this reaction, this entire reaction of that hydrogen which is happening on this side of our material is shown here. And you can see here that basically hydrogen comes in contact over here. That is our hydrogen come in contact with that platinum, and then they give us 2 electrons, and that electron is going to transfer here like this. And when they reach here on other side, then what happened? That is our positive. then the reaction is happening. Okay, and now interface of electrolyte and electrocatalyst. Oxygen is coming here, and then they are going to take these electrons, and hydrogen is coming from the nephron membrane. Now this shaded area that is a little gray, that is a nephron membrane, and that nephron membrane basically act as a transfer of that proton, because they exchange the proton from this side to this one. So that's just a very simple assembly. What you have to do, basically, you have to prepare that membrane, and that membrane must have some comparatively related characteristic of that of nephron, which must be cheaper than this one. Maybe the activity is not as high as it is, but the cost is quite low, then it's also acceptable. If the activity is also high, the cost is also low, then that is a great breakthrough over there. So that is just a simple overview of the whole, and that is the individual cell, which is shown over here. You can see here there is a hydrogen is entering at one side. Now if there is any residual hydrogen, they can come out through this, and this scrubbing material is our negative. This is our negative electrode, is shown here. Okay, and that is our positive electrode, is shown here. And on this side, oxygen goes here. Now oxygen and our byproduct, it is a residual oxygen, is come out through this. Now polymer electrode, that is our polymer is here. So basically that is this one is our negative electrode, which is written here, and that is our positive electrode, which is written over here. So, and that is membrane electrode assembly, MEA, that means membrane electrode assembly, that is arranged in such a fashion. So basically that's not difficult to design, not difficult to work, but to get a desired output from this, that's really hard. And this individual cell we are going to connect in series, and when we connect all of them in series, then we can take a proper or desired output from that of the thing. Okay, so till now we had studied different kinds of cells, uh, and basically we had just studied there are different assemblies, that where is cathode and where is anode, and what is in between cathode and anode, and is it possible that we can get some potential from individual cell, and what is the normal or nominal operational temperature for different cells, for alkaline fuel cell, for phosphoric acid fuel cell, and for membrane fuel cell, that is polymer membrane fuel cell or proton exchange membrane fuel cell, and what is the basic differences among all different kinds of cells. So if we just have a quick look to all of these different kinds, no matter that either in between the cathode and anode is solid, liquid, or gas, or whatever the case may be, but the basic procedure is the same. One of the most important thing that we should need cell operation, that how cell can operate. So basically it's converts of electrolyzer that convert chemical free energy into electricity. Now fuel is oxidized at negative electrode, and that we had discussed in many of our slides, that fuel is going to oxidize. Like if we are going to use hydrogen, so we name that as a hydrogen oxidation reaction. Okay, so that's the first one, is the fuel is oxidized at negative electrode with the release of electron that passes through the external circuit and reduces oxygen at positive electrode. And this kind of reaction, which is happening at positive electrode, we call them oxygen reduction reaction. Okay. Whatever about this, the negative electrode reaction, I will write here, that is hydrogen oxidation reaction, HOR and ORR. Now the flow of electron is balanced by the ionic current, that is electrical charge carried by ions. Of course, whenever there is a charge going from one electrode to another electrode, how it can be counterbalanced? It can be balanced by these ions inside the solution in the electrolyte. The reversible voltage V are produced by the cell, that is when there is no current flow, is known as open circuit potential, and it is given by this equation, that is minus delta G divided by NF. And you can also write in another way, that is delta G is minus NF E. You can also write E as a potential R, that VR, which is written over here as a reversible or open circuit voltage. So that's the equation that which can just tell us about that, about the reversible voltage. It depends upon on the number of electrons, inversely proportional to the number of electron flows, and also to the delta G, that gives free energy. Okay, F is the Faraday constant over here. Okay, now here, when you look at this, the cell voltage is plotted versus current density. That is the cell voltage on our y-axis and current density over here. And as current starts, uh, if we are just taking starting from here, so as the current is drawing, there is 0 0.1, then 0 0.2, 0 0.3, slowly and gradually. So the voltage falls. Well, there is voltage fall. You see here that initially it's this value, then after 2 it's this value, then after 0 0.4 it's have this value. So there is a gradual fall in the voltage. The factor that contribute to loss in the performance is reflected by the different region of that curve. There are, if we just broadly divide it into three fragments. So, okay, so we have this first fragment of that curve, and that is the second fragment and that is the third fragment. Okay, so there are three fragments. So I have just, this one is up to here, and the second one is up to here. Okay, and the third one is still here. So basically there are three different factors that can contribute to the loss in performance. That is the voltage drop, and that voltage drop basically initially, when there is a small current drawing from here, that is due to electrokinetic limitation, and that we have studied already in basic chemical reaction which is happening at the interface of any catalyst or any electrodes, that we have studied that before. The second one is due to ohmic limitation. That is the middle part. But you can see here that basically the reversible voltage under standard condition is 1.299 at 25. Okay, and drawing current from the cell. However, the voltage developed is much lower than this, is typically 0.6 to 0.8. If you just note here, the 0.8 is like this, and that is 0.6. So that basically refers to the middle line, and that middle line, you can see here, there is not enough drop in the voltage over there. Basically, there is a sudden fall over here, and this position here, that's quite slow. So the condition for the reaction, that is, we can just consider over here for hydrogen oxidation, is 1.29 volt. Okay, so 1.29 volt, you can just remember from this point that the initial fall is, why there is initial fall over here, and why this fall, and why this one. So basically there is explanation for everyone. The initial fall is due to that activation, that we need our material to get activated. When it get activated, then it goes through a chemical reaction. Okay, now whenever the material is not activated, you should just keep in mind like this kind of curve. So when the material is not reached here, how is possible that it can give us some products? So until and unless you take the material out of that bulk and they get activated, they reach to this activation barrier, cross this activation barrier, then there is a possibility of either oxidation or reduction reaction. But whatever the reaction may be, the reactants is going to convert into product. It's not possible to convert into product until and unless they cross this barrier. Okay, so that is very important for this, and that's happening during the first portion of that curve. Now the central is ohmic losses. It play a more significant role, that arises from resistance to the flow of ions in the electrolyte. So that's also very important. That is the ions in the electrolyte. And finally, the mass transport limitation, that is concentration limitation. It can be represented by this, which result from gas consumption, outstripping supply becomes a dominant at high concentration. There are also electrical resistance losses in the collector and conductor of the current. There are possibly side reaction and maybe leakage of ions and current between the series and the connected, all of which may contribute to the voltage drop. But that voltage drop may count it as uh, it may be counted either due to electrokinetics limitation or ohmic limitation or mass transport limitation. So that's important one. The second point over here that if we are going to plot the cell voltage versus current density, you can also see here a power density here. And the maximum power you can attain here, initially as the current run, the power density is increasing. And we peak power over here, and you can just see here, it's just in between there 0.6 to 0.8, up above 0.6 voltage. So that's about the power voltage. Okay. Now, referring back to the voltage versus temperature relation of water electrolysis, if you just keep in mind that there is a water electrolysis, uh, it will be apparent that only free energy of the reaction, that is a energy, is a gives free energy for the conversion of electrical energy, whereas entropy is represent the energy that lost in the surrounding. So it means that is the heat in the form. That is basically this heat, and that is the available energy for the chemical reaction. The higher the temperature, smaller will be the voltage developed, and the larger will be the quantity of heat evolved. Now, this is a very technical point over here. Uh, the higher the temperature, if we just keep in mind, the higher the temperature, the smaller will be the voltage developed. Okay, and the larger will be the quantity of heat evolved. It depends upon on the temperature. Therefore, the optimum output of the electrical energy fuel cells are the best operated at low temperature. Okay, but the kinetics and electrocatalytic effect, uh, they have lowest practical temperature. So again, there should be a compromise on certain factors. Now, fuel cells that run at high temperature are best developed for CHPs. If you remember, initially we have discussed that the CHPs schemes are combined with the gas turbine uh, as to make a maximum use of liberated heat. And that we have initially discussed that there are some sectors of fuel cells they need to be improved. And the most important one is for ORR chemical reaction. We are searching for some suitable catalyst, and the second point that we are searching for that heat evolved. If we can easily use that heat in some useful purposes, then maybe we can increase the efficiency of that fuel cell up to 80%. So that's the most important one. Now here is the just combined view of different pictures that is given in this plot. We have different kind of cells, fuel cells, and that different kind of fuel cell is alkaline fuel cell, one that you know about this, and the second one is proton exchange membrane fuel cells, and direct methanol fuel cells, and phosphoric acid fuel cells, and there are other one that is MC metal carbonate fuel cells, and that is solid oxide fuel cells. Now, all these different cells and their half cell reaction is given here in these slides. Now, you can see everywhere in most of the cases, you see what about the cell reaction at cathode and what about the cell reaction at anode. So here on this slide, what the reaction is given, these are the reaction happening at this electrode. And what the reaction is happening here is happening on that electrode. Okay, and what is inside between, you can see here a quick look to that one. Now, in alkaline fuel cells, you know that we are using some alkalis, and that is potassium hydroxide or calcium hydroxide. So of course, when they are going to split, there must be potassium and there must be a hydroxyl ion. So that's a reversible reaction. Okay, so that's quite convenient that you can easily understand that. And what about the reaction here? Now, here is a hydrogen and a hydroxyl. That is, hydrogen is going to split. And that hydrogen, after splitting, they give us electrons, and that electrons can come through this way. And here, that oxygen can take the electron and they can convert it into OH negative. So basically, the mechanism over here, you should just keep in mind the mechanism that what is happening and what's the end product. Okay, and what about the polymer exchange membrane, proton exchange membrane fuel cell? You can look at this picture. So proton exchange, again, there is a water split, hydrogen splitting, into proton and electron, and on this side, there's the product as well. Now you can see at the methanol and ethanol, what's the product over here? So there is also a product that is carbon dioxide, and there is acid or polymer that is over here. Then this is a problem, that how we can handle to this carbon dioxide. Now on this side, generally you can look at this reaction, that is just oxygen reaction. And oxygen and that proton which is coming from this side, so the proton is combining with that oxygen and they can give you the water as well. In case of phosphoric acid fuel cell, we have studied that chemical reaction, again the same. It's quite simple. And on the right hand side, you also see it's oxygen. One thing is very common, no matter whatever the case may be, and no matter which type of cells, again there is only oxygen that is used. And they are consuming that electron which is available. That's common over there. And the most of the product you can see there are water. In here it's hydroxyl ion, and here it's carbonate, and here is oxide, but in most of the cases you can see that it's common. So that is a general overview. So that was the general discussion about the fuel cells. Now in this slide you can see that there are different application of fuel cell, and there are which kind of fuels we can use. So that's in the center we have fuel cell, and now above this line, we can see here that which kind of fuel we can use. Hydrogen we can use as a fuel in proton exchange membrane fuel cell, and that is alkali fuel cells, and that we had studied in detail. Now, methanol or ethanol, we can also use as a fuel in fuel cells. We call them direct methanol fuel cells or direct ethanol fuel cells. We can also use that. Okay. And what's the consequences? What is the side reaction that we had studied just in the second last slide? Now we can also use biogas as a fuel, biomass as a fuel, coal, natural gas, petroleum, and then we have different categories. You can see solid oxide fuel cells, and we have different, that is phosphoric acid, and that is proton exchange membrane, and different kinds of the fuel cells that that is a broader spectra. So it means in the fuels, we are not restricted to use one kind of fuel. The second one, we are not restricted just one kind of mechanism over there. And there is a broader range. Now, the third one, we are not restricted even to a single temperature, that at this temperature our fuel cell will work. So we have different temperature ranges, we have different fuel varieties. So there are a lot of application over there. Now, what about its application? So as I told you, there is a portable device, transportation, and stationary system. And that we had studied in detail, that in the portable devices, that it can, in the laptops, that there are some Japanese industries, they are preparing some fuel cell for laptops, cell phones, and some other devices, electronic devices. For transportation, in the road is also okay, sea is also okay, and in the air. So we can also use, so there are different examples. For the road, I told you that there are some different examples for hydrogen fuel cells. There are different buses running by hydrogen. And the sea, there are submarines, and air, space shuttles, and the stationary for some residential areas and industries. Now, the last point that I want to conclude the whole discussion over here, that what we basically understand from the fuel cell, that it's quite convenient, it's economical. Why it's economical? The reason behind this is in most of the cases they are using hydrogen, and hydrogen is the most abundant element in the universe. That's the reason that we can claim that it's either we can use direct hydrogen or hydrogen carrier fuels. So these are the second point. It's environment friendly. How we can say it's environment friendly? It's environment friendly because in most of the cases we know that the product or the byproduct is only water. Even if they can release some sort of carbon dioxide or some carbon dioxide containing, like in carbonates, it's much more, that is comparatively less as compared to other technologies. And the third one, it's environment friendly because it's working in a silent mode. It do not disturb any of the sidewise residential buildings or official buildings or any college, schools, universities. So it's quite silent. The fourth one that is most important one is economical because you see that there is no movable parts in the fuel cells. So they don't lose heat as the turbine or as the internal combustion engine they can do. Still, there are some problems. So I'm sure that some of you will come forward and they will try to solve the problem. At least if cannot solve the problem, so at least you should try to solve some of the problem regarding the fuel cells and regarding the energy sectors. I think is enough for today. And thank you so much for listening me. Assalamu alaikum wa rahmatullahi wa barakatuh.